I'd like to welcome everybody to our talk about image registration and image stitching. It's my pleasure to introduce my colleague David from Armenia. He's going to talk about image registration, about the technicalities of getting two or more images congruent. And I'll take over the second part where I will talk about the workflow in order to achieve image stitching. So, David, please, it's all yours.
Yeah, hello, everyone. Thank you, Marcus. Let me start with image registration. My name is David Bagdasaryan. I work as a consultant in Wolfram Research. I will be talking about image registration. Let us start with defining the image registration term. It is the process to transform one image to the coordinate system of the other. It is core computer vision problem, and many other computer vision tasks depends on that. And there are two main approaches to do image registration. It's sparse and dense. The dense methods are often very slow due to search of the transformation in high dimensional space. And the sparse methods using only special points in the image, so they are much faster than the dense methods. And we will be talking about those sparse methods, which also called feature-based methods. In the next slide. Nowadays, the researchers try to create end-to-end solution to image registration, but it's not yet outperform the classical step-by-step solutions. In Wolfram language, we have image align superfunction that doing the whole alignment procedure. But how it works? The classical registration pipeline is first detection, description, matching, transformation estimation, and then image transformation. So we start with the detecting informative points in the images, in the two images or more. Then we describe each image with the special vector that's called descriptor. Then we try to match those descriptors. After those matches, we estimate the transformation and apply those transformation on the image, getting the aligned images. And each of that part of the pipeline has the system function in Wolfram language. This is the image key points that can be used for detection and description. And this is descriptors, image corresponding points for matching, and fine geometric transform for estimating the transformation. But what are the key points? The goal here is to extract distinctive and invariant to some transformation points. Several algorithms available as methods of image key points, and here we list some groups of algorithms, and image kernels also can be assumed as an image key point detector. For example, Harris kernel detector, which available as kernel filter in Wolfram system. The next category would be second order derivative based, which means that it uses image gradients in two perpendicular directions, and tries to find the local extrema there, and that local extrema would be a key point. And there are another category, intensity-based methods like fast, Agast, and the others, which are often very fast algorithms, and they do comparisons, binary comparisons between the given pixel and surrounding pixels. For example, fast takes the 8 pixels around it and represents that as a byte, that feature. And the last category is neural network based, that tries to not to invent the features, but to learn them during the training and to perform detection and description at the same time. The descriptors, how the descriptors work. The SIFT surf based uses the gradient statistics to calculate those descriptors, which is computing the orientation for around the detected key point. They take the patches of the image and compute the orientation in each patch, and then do histograms of that orientations, which become the descriptor. 4x4 arrays used in SIFT, for example, which is 8-bin histogram for each, giving total 128 features. And as I said, local intensity comparison-based method like Kaze or Brisk uses this comparison between the pixels intensity values to create those descriptors. At this point, we talked about two properties of the key points, is the position and the descriptor, but there are some more. I will show you with this example. There are strength, which is the measure of quality of the key point. There are scale, which is the increasing size of the key point, orientation, and the others like contrast sign, which is red and yellow here. Note that the red one around is put it not in the some feature points like we think, it's in the middle, so it's also considered feature for that SIFT algorithm. Yeah, only those key points that have descriptors would be valid for the matching. So not all of them have support for all of the features listed. Here is the table that shows which support which. And the next slide shows that we discussed that the descriptors have to be invariant to certain transformation, and this manipulate shows some small example that we change the parameter here, for example, the translation, and we see how the match stays more or less invariant. In real world scenario, it may be not fully invariant to the transformation, but it tries to do that. Scale is incorporated in SIFT algorithm, so it's much more stable in terms of matches here. Brightness, we can tweak the brightness and see that it stays, the matches stays here. So like those matches allow us to assume that the key points would be close in the feature space if they are correspond to the same point on the image. So this we can match the key points. Each key point uses each metric to compute the distance between these two. The main metrics are Euclidean and Hamming. And the first thing that we can think of how to do that is for each key point compute the descriptor. For each key point descriptor, we can compute the distance for all the key points and take the best one. That would be nearest neighbor approach. And this works for some level. But the better solution for that problem is to take the ratios between first and second descriptor distances. This is much more robust and is typically used worldwide. So here is the example of the match. Here we matching the key points for these two images of the moon. And the next problem in the pipeline would be to estimate the transformation. And to do that, some parts of the images may look the same, and that's why we can have wrong matches. So we have to estimate some transformation, having that we have some portion of outliers, and for that we have to use Ranzak iterative algorithm that can deal with that outliers. Fine geometric transform actually would solve this problem and can automatically pick the proper method in proper transformation class for doing that, solving that problem. And in the end of the pipeline, we have to, when we have the transformation, we would want to apply that transformation on the image, and the image perspective transform would give us that possibility to apply the calculated transformation on the image. So that is the pipeline of how the image registration is in the Wolfram language, is supported through this functionality. So at this point, I will give my talk to Markus.
Okay, we have to unshare quickly.
Yeah, sure. Thank you.
Maybe while switching, I'd like to point out that we do have new key points in the pipeline for version 13 that David implemented, most notably sift and root sift. And furthermore, also you can find in the network repository already a page about the D2net key points that are based on neural networks. So that's a new direction we pursue as well. All right, now that we know the basics of at least sparse registration, I'd like to quickly apply the knowledge we gained to a very nice and fun application that's image stitching. So the idea is to basically take an image or actually several images and plug them together to create a big panorama. And now, okay, now try to move and okay, finally got the new slide. Now, first, before I proceed, I'd like to say what stitching is and what it isn't, because there is a very enticing other related topic, and that is 3D reconstruction that also takes several images as input and then produces not just a combined image, but a 3D model. Now, for those of you who are into this and who are looking for this kind of application, I did copy over here a marketing example where we have shown how to, for example, take 3 images. The parallax of these 3 images allows you to calculate a depth map, and then you can create a kind of a 3D model from what you have taken as a photograph. Now, this is not what I will talk about. For those who are disappointed, A, please bear with me, and second, you can play with the code of the example I just showed. Instead, we are just focusing on the scenario where we don't gain any depth information by combining images. That's, for example, the case if you, let's say, take several images through a microscope and you move the stage with the sample sideways. You can take a new image and thereby basically pick up an array of images that you then combine to a large image. Now that would be stitching. It would not allow you to obtain any depth information, but just a bigger image. And that's exactly the topic we will tackle here. Okay. Now, the constraint that we do not want to engage into depth information means that we have to focus on 2 scenarios. And the scenario, the first one, which is probably the most or best known one, is the scan mode. The scan mode basically means that you're looking at image data that you can assume to be on a plane, more or less, let's say the surface of the Earth, or a document that you scan, a page. There you can move with your camera across the page. You can, okay, so much for running something. You can move across the image and take different images from different vantage points. And all of this is assumed to be on a plane. So no matter how you position and how you direct your camera, you'll eventually pick up image data on a plane. Now that's the scan mode, and the other mode would be a panorama mode, and that is basically not assuming that the image data is in a plane. You can have objects in the image or in the panorama that's close, stuff that's further away. The way you make sure that there's no depth information screwing up your stitching essentially assumes that you do not change your viewpoint. The vantage point from where you take all the images should stay the same, and the only thing you do is essentially turn your head or turn your camera and thereby change the viewing direction, but not the viewpoint. And thereby, essentially, all the light information that comes to you essentially gives you one dot on the surrounding sphere. And there is no parallax or anything like that that would allow you to derive the depth of the information or depth of the image. Now, these are the two scenarios we'll look into. And in the course, before I forget to mention that in this course of this talk, I will focus mostly on the panorama mode, simply because I don't have time to do scanning and panorama mode. The scan mode is a bit more trivial, and so I'll opt for the more complicated one. Now, clearly, when we go from one image to the next, we have some kind of spatial transformation, and as you may know already, using find corresponding points and the like in Mathematica, we have different transformation classes to choose from. Now, simple ones that are probably self-explanatory are, let's say, translation. There you just essentially move one image over the next. You move it left, right, up or down, but you don't rotate, scale it, skew it, or anything of that sort. Now, these are the transformation classes you may want to apply when you do microscopy stitching. Then there's rigid, that includes rotation, similarity, affine. And then the most interesting one for us to do a panorama stitching is the perspective transformation class. Now that transformation class is the biggest one of all the linear transformations that we can look at. It basically has 8 parameters because you're looking at linear fractional transformations. I just basically, in order to avoid now any kind of detailed mathematics, I'll just show you the transformations possible. You can rotate the camera around its optical axis. You can tilt it to the left, tilt it to the right. You can then rotate after having tilted. You can move to the left. You can move upward, downward. And furthermore, these being the 6 motions and rotations you can do with your camera in 3D, you can furthermore vary the distance to the projection surface, and you can also tilt the projection surface if you want to. So these are essentially the 8 degrees of freedom that you have in a perspective transformation. And when you stitch or try to register 2 images, these are the 8 dimensions or 8 parameters that you need to specify. Now that is somewhat incorrect, this claim, because strictly speaking, when I'm looking at the 2 scenarios that I just mentioned, I do not utilize the full 8 degrees of freedom of a perspective transformation. But when I do scanning, I essentially just move, let's say, the camera with respect to the first camera position. I can redirect the viewing direction. Basically, I have here 3 translation degrees of freedom and 3 degrees of freedom when it comes to rotation. So essentially, I just utilize 6 degrees of freedom because I do not assume that the plane that I scan changes in any way. Now, that's one restriction, but since we do not follow up on scans, I have to focus more on the second case here, the second constraint, and that is the panorama transformation. Now, in the panorama transformation, we assume that all the images coming in are essentially just due to rotations of the camera itself. And that means, oh gosh, I have to, for whatever reason, reevaluate. And then I can move, wait a minute, I can move one camera around, I can turn it, I can rotate around its own optical axis. And I can do one thing, I can basically change the focal length, or basically the size of the viewing angle, or if I'm looking at a wide angle or a zoom teleobjective, and that means I can enlarge the screen or make the screen smaller in relation to the other screen. And these are the possible scenarios that I'm looking at. Okay, I think I know what I have done wrong here. Hold on just a second. I just have to reevaluate in order to get my initialization cells running. Yes. No, still not working. Okay, for whatever reason. Okay, next slide. Okay, so what I just said, we are now going to apply to the idea of image stitching. And as you may have seen yesterday in Stephen's talk, this is what we're looking at. We want to have a command image stitch, which will be available hopefully in version 13, that takes any kind of images or set of images, either as a bag of images, simply as a list of images, or if you know some connectivity between the images as an array of images. You just throw that command, this list of images into the command image stitch, specify if you want to have a scan or panorama set to work with. And in this case, it's definitely panorama. And what you get back is automatically a stitched image of the scene that you have provided in these images. Now, instead of just basically saying, voila, this is what you get, I very quickly like to run through the process of generating such an image because the most fun actually is the math involved in here, and it's not just registration. So the pipeline we run through, and which you basically can run through once you download this notebook, because the code is in this notebook, is some pre-processing, feature detection, the key points we just learned about, the feature matching, then finding the local transformation estimations between two images. Out of that, of a network of transformation, constructing a global network, then making sure that the color and brightness between images does fit, choose a common projection space, and then eventually blend the stitched image together. And okay, so now please bear with me. This is going to be somewhat a tour de force going through all of this. The first step is to quickly remove optical distortions in an image, because strictly speaking, what you should have is that straight lines in an image should be straight lines. But what could happen is if your optics isn't great and your lenses deform the image, you get these kind of cushioning effects. And they are pretty bad for image stitching, especially when you assume linear transformations to be the middleman between images, and images tend to overlap here on the side. This is where the nonlinearities would kick in. So pre-processing step would be to undistort images with a kind of image distortion command that is supplied here. Okay, I'm in the pedal. For whatever reason, things are not working out. Let me try again. Quit kernel. Load images, sorry. The machine is giving up on me here. Okay. Yes. Perform the image distortion. Okay, now it's working. Then I can see here the dimensions of the array that I have provided. Essentially, it's just a list. I've included 9 images, and then basically it means when to stitch these images, I have to basically work through this stitching graph, which basically means that every node here is an image, every link is a potential connection overlap between two images, and I can now populate this graph with images, image key points and the like, and try to derive the corresponding edges and their corresponding transformations. And that's exactly what I do here. I load now an association database for all the vertices, all the information of the vertices of this graph. And furthermore, I do the same in a second for all the edges. Now, quickly, a remark regarding the potential danger that you encounter when you do image stitching. First, you may have areas where there are no key points because they're just too dull, like the sky. You may have problems with areas that change very quickly, like the surface of water. Now, these waterways change very quickly. So from one image to the next, the whole pattern here will have changed, and there's no quick key point relation between A and B. You will have images where the classical key points don't really kick in because they can't find any features around these bright little points that make up the stars. You have to work on different features like constellations, local ones. And then you have issues like images may be too small, like a 64x64 image may be too small to do image stitching simply because the boundary effects kick in and they don't allow you to pick up any key points. Now, having looked into that, I do now for every node in that graph, I calculate my key points. Basically store them all in the association, all the properties, the position, the descriptor, contrast time, and strength of those served key points. And this is where I store them. And then for every vertex, I essentially have then stored an image, the key points, the key point position, strength, and descriptor. So at the end of the day, I have now for every image node, the image and all the key points. And the next step would be to find now matching key points. So I always have to look at image pairs. So I'm looking now at edges, the links between two nodes. And there I look for common key points. And if I find less than 4, I can rest assured that I didn't find enough to populate the edge. And you already see that the graph got much simpler. Now only neighboring images essentially still have an edge left that I can further process. Then I can do ransack, basically verify if the matching key points also satisfy the transformation class in question, and just throw out all the edges that don't live up to it. Then I load in all the essentially one parameter of the transformation that I estimated with the perspective transformation, and that is how many pixels I have to move across an image to basically rotate a certain angle. So that is essentially the number of pixels per radians. It's just the same as an estimate of focal length. And I assume this to be the same in the entire set of images. And then I estimate now only those parameters in the perspective transformation that adhere to just a camera rotation and not to all the other degrees of freedom. And that leaves me then with just one transformation between per edge. So every edge now has a transformation function that describes how to get from image A to image B. All right. Come on, new page, new page. Okay, here we go. And then I have to not just get the spatial fit correct, but also have to fit the color. And I do this by basically looking at overlapping regions of an image, taking image A and image B in, transforming one image on top of the other, looking at a histogram transform that basically maps all the colors of one image to the corresponding colors of the other one. And that allows me to have different brightness levels, different exposures, different images to be equilibrated. Now, this would be the stitch without it. And this would be the stitch now with this equilibration. And so wait a minute. Come on, new page. And last but not least, I have to verify how many links I have left in my graph, throw out all the disconnected ones, and then I can look at the graph as it is right now. And this is my graph. The strength of the edges basically give me the, okay, I'm running out of time, so let me quickly finish up. The strength between the images, and then I can basically construct a tree that allows me to go from a central position to all the other nodes and stitch them together. And this is what I do here. This is essentially the tree from 6 that I go after to find all the other nodes. I run the transformation obtain all the transformations for every edge. And then I have to look for common canvas, either it's a plane or a cylinder that I can project on. In this particular case, I take a plane. I have to look for the best direction to position that plane to get everything on. And I do that by minimizing the largest angle to all the corner cases and find a direction that is optimal to host the entire stitch. Find the transformation, attach the transformation to all the other transformations, derive the plot range, and then last but not least, I can display the entire stitch. So this is a kind of the technology summary of what you find beneath the network, but beneath the command image stitch. Last but not least, what you'll then have to do is blending. So if you have two images and the transition shouldn't be too hard, you can blur the transition, and that's called feathering. Or you can do a much more elaborate thing, and that is merge those via a Laplacian pyramid, image pyramid, and thereby you blend them at every scale separately, and that gives you a transition that looks almost natural. And last but not least, you could even consider in-painting as the last resort in order to finish things up. Okay, let's skip that page. And this basically brings me to an end about image stitching. This is just a rough draft where things are going. And if you have any questions or suggestions, please be my guest. All right, given the fact that I have gone slightly over time, I'm not sure if we have now time for questions. If anybody wants to speak up, I'm monitoring the participant list. No. So I don't see anybody raising his or her hand. So I assume we do not have any questions. In that case, thanks for attending, and please download the notebook because that will allow you to do stitching yourself even without version 13. Thanks a lot.